Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Folks, we're going to look at example 433. Internal design pressure. We're going to look at spherical heads, very interesting problems. And we're going to continue. We're going to start with the Section 8 Division 1, what it says in that standard. And we're going to be looking at the code case 2695, what's allowed in from Division 2 to be used for this kind of analysis. And a reminder that the allowable stresses must always be the VIII-1 allowable stresses, and bear in mind that this is all going to come from the ASME PTB-4 2013 manual, and it's part 4. And so we're going to follow that example quite closely, and but we're going to deviate a little bit just for some more clarity and to add a few extra points. So let's continue. But we're going to continue first of all with Section 8 Division 1. So as per usual, we set up our table, and we have our values shown here. This material is more typical of spheres, so we use that, and you can see the diameter it's not a huge sphere, but it's 149-inch ID, and in this case there's no corrosion allowance. And because that's a gas probably, and the joint efficiency is 1, and the pressure is 2080 psi, and it's quite hot. We're at 850 Fahrenheit. Here from the example, we're going to look at UG27D, and we're going to look at the paragraph. This is from 2019 edition, I believe, and it says, when the thickness of the shell, wholly spherical vessel, which means it's just a vessel, there's no transitions in it, it must not, for these equations to apply, it must not exceed 0.356 R, or P does not exceed 0.665 times S times E. The example doesn't really get into that, and it should. So you can use this equation here to calculate your thickness, and you can once you determine your thickness and you add your closest nominal size, then and your minimum thickness, then you can calculate your maximum allowable working pressure for the sphere components. So we're going to continue on to design of welded joints UW9, and any reduction in thickness within the coarse shell or spherical shell shall be in accordance with UW9. And so basically, if you go through that, some of the key points is, you have to use the A, B, C, or D permissible type of joints. You have to use grooved welds, and there's a part about taper transition specific rules and about radiograph joints. So be aware of that and go through UW9. Also, there's some rules about lap joints, welded shapes subject to bending that you have to review, and the minimum weld sizes and the offset joints. Okay, so we're going to look at the offset joints in a spherical head. Okay, so basically the rule is, this is like one of the key rules of it, is for joints connecting hemispherical heads to shells shall follow the following. T must be equal to at least 3/8 of an inch minimum. And the maximum difference in the thickness between T, like the thickness between T or this, is 2.5 millimeters. Okay. And we use figure UW29 9-3 for joints connecting hemispherical heads to shells shall be noted on the manufacturer's test report, which is I guess that's standard So let's take a look at the preliminary calculations. The allowable stresses at design temperature. We got section 2D table 1A, and we pulled that out of that one. And we can also use like table 1D as well, but this is for the section 2D table 1A, and we got 21,000 psi. We adjust for the hydraulic head. In this case, there is no adjustment on hydraulic head because it's it's a gaseous sphere. And we're going to continue on here with the method 1 calculation. So we're going to make our adjustments. We're going to calculate our inside spherical L. And so we have to take into account the corrosion allowance and make that adjustment. And then we're going to do our first little litmus checks to see whether these equations are valid. The first check we talked about earlier is using that ratio of 0.356 times L. And I just wrote the logic in my spreadsheet and just said it was valid. And then I went to the next one here and did that second test, and it said it was valid as well. This has to do with thick and thick, biaxial or triaxial stresses, and for thick and thin type shells. So this says that we can still use this. So we're going to continue. So this is just the equation for a sphere for calculating thickness, and we calculate 0.372 using the pressure and the adjusted L, and the stress and the joint factor and the pressure again one more time. And then we adjust for the corrosion allowance, but in this case there is none. And then we continue. So it's a fairly thick shell. So we're going to continue on, talk about the limitations. So we have to be aware of local thinning, and that's something the manufacturer looks at to ensure that they meet Appendix 32, and that there's a minimum thickness requirement also, which we alluded to earlier. And there's rules on under tolerance for the plates as well, and rules on the corrosion allowance. So that's about it for that one. Got a spherical shell, and we're going to look this time at division 2. So the code case example, they use this equation with the exponent in it. It looks very similar to that of a shell. And in the first part here, we make the adjustment for the diameter, considering the corrosion allowance, because we have to use the final thickness in the design. And so we do the calculation, and we determine 3.782. So let's go to the final slide and see how they compare. And reminder that the stress allowable is the same for this calculation as the division 1. So let's look. So we got 95 millimeters, 3.7264, and 96.1, which is 3.78. So they're essentially the same. Obviously, there's no advantage of using the division 2, and it's a lot of extra paperwork. Is it worth it? I in this case, definitely not, but it's allowed.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.